Okay, let's try finding the particular solution of the following differential equation. Second derivative dy dx square minus 2 dy dx first derivative plus y equals to 2x square minus 1. So clearly this is a non-homogeneous problem. So this differential equation must also meet y equals to 1 when x equals to 0, as well as first derivative dy dx equals to 2. So let's proceed by starting with finding the characteristic equation of the differential equation. So I can just write the characteristic equation to be m squared minus 2m plus 1 equals to 0. So this is come from basically the equation of differential equation. It's that one. So m squared minus 2m plus 1 come from the constant, from the variable y. So you ignore the non-homogeneous part at the moment. Okay, we will just leave it for the time being. So we have a quadratic equation of m squared minus 2m plus 1, which we can say that the roots, okay, will be ,1. So it is 1 and minus 1. Therefore the roots are simply 1, or we have equal real roots in this case. Therefore our general solution, the complementary function, okay, therefore the complementary function will have a general form of, if you like, yc will have general form of a plus bx times e raised to the power x. Let me just have to write down. So this is actually come from yc equals to a plus bx times e to the power of mx, where we have our roots to be equal and real. So m in this case equals to 1, as you can see previously here. So we just plug the equation into the formula yc equal to a plus bx times e to the mx, so m equals to 1. And now we can proceed with looking at the non-homogeneous part, okay, which is 2x squared minus 1. So this is come from the green part, the highlighted green part here. Let me also highlight into green color. So based on this equation, then our solution, okay, because the non-homogeneous term here is basically a polynomial of second degree, then our solution, particular integral, if you like, the particular integral yp will be in the form of general form of x raised to the power of r times ax also to the power of 2, in this case the same order, plus bx plus c. So bear in mind that the 2 here, because of the same, must have the same order as the original function, and we have to find the least minimum r value starting from r equals to 0. Then yp will become x to the 0, ax squared plus bx plus c, which is same as saying ax squared plus bx plus c as our yp, and by comparing our yp with our yc, we can see that if you like this and this, there are no terms, or there are no terms that are common between yp and yc. As you can see here, the first term is ax squared, and then bx, the third is a constant, and then in yc we have, let me just write it, a times e to the power of x followed by bx times e to the power of x. So I should not highlight that. Okay. So you can see that both yc and yp contains different terms, and therefore we can proceed by finding the first and the second derivative of yp. Why we do that? Because we are going to plug the first and second derivative into the main differential equation here. So the main differential equation contains the first and second derivative, as you can see here on the first term, second terms are the derivative, the first and second derivative. That's the reason why we need to find the first and the second derivative of yp also. So dyp, first one, over dx, then it will be 2ax plus b for the first derivative, and for the second derivative of yp would be 2a. So substitute, by substituting, substitute 1 and 2 into the main b differential equation, which was this second derivative dy dx minus 2 dy dx plus y, yeah, plus y equals to 2x squared minus 1. So we have our first and second derivative. So this is our second. Let me highlight it in, for example, second derivative with blue, and the second of the first in pink. Okay, so this is the first, so it's gonna go there, and then zero derivative is that one. So let's plug it into the formula, into the function. We have the second derivative to be 2a minus 2 times the first derivative, which was 2ax plus b, as you can see that. Okay. Plus the first of the non-zero derivative, if you like, which is ax squared plus bx plus c, and the whole thing is equals to 2x squared minus 1. So after rearrangement, the whole equation will become ax squared plus b minus 4a x plus 2a minus 2b plus c equals to 2x squared minus 1. So again, by highlighting a couple of terms here, for example, the x squared, this is x squared, and then the x has no correspondence on the right hand side, and then our constant -1 equals to all of constant on the left here. So after we equating the coefficient, we have for the x square coefficient, we have clearly a equals to 2. You can see here a equals to 2, and then for the x only, we have b minus 4a equals to 0. Therefore, by plugging the value of a, then we will get b equals to 8. And then for the constant of x, this is x to the power of 1, this is x to the power of 0, which is a constant. We have 2a minus 2b plus c equals to -1 from the pink part here. So by plugging the value of a and b respectively, we will get the value of c to be 11. So our particular integral yp, therefore yp equals to the value of a is 2x squared plus 8x plus 11. If you remember, the value of yp was as ax squared plus bx plus c. So if you want, I can rewrite like this, put it bottom there. So yp equals to ax squared plus bx plus c, and therefore yp equals to 2x squared after finding the value of a. Okay, to b equals to 2, and the value of b equals to 8, and value of c equals to 11. So our overall solution for the differential equation will consist of yc plus yp. So we already know the yc to have a common form of a plus bx times e to the power of 1x, which is x, plus our yp, which is 2x squared plus 8x plus 11. So in order to find the value of constant a and b, we need to plug in our initial boundary condition. So we also need to take the first derivative, okay, because we given the initial condition of initial condition y is equals to 1 when x equals to 0. You can plug this in. So if we plug this in, we will get the value of a to be -10 by simply plugging the value of x equal to 0 to everything. Okay, so we will get, in this case, y equals to, just write down here, y equals to a plus b times 0 times e to the 0 plus 2 times 0 plus 8 times 0 plus 11. So you will get a y in this case already equals to 1. A is still known, plus 0 times 1 plus 0 plus 0 plus 11. Okay, from here give you a if you continue, we already given the value of dy dx equals to 2 when x equals to 0. That's the reason why we need to take the first derivative of our equation here that I highlighted here. So the first derivative of that, dy over dx, is equals to a plus bx times e to the x plus b times e to the power x plus the quadratic equation is 4x plus 8, and dy dx according to the given information equals to 2. So when the value of a is already given, we already obtained a equals to negative 10, and x here is 0. Negative 10 plus b times 0 times e to the power of 0 plus b e to the power of 0 plus 4 times 0 plus 8. So you will get the value of b to be equals to 4. Equals to 4 and a equals to minus 10. So the overall equation we will have, it was originally a plus bx times e to the power of x plus 2x squared plus 8x plus 11. So we already find the value of a to be minus 10 and value of b equals to 4. Therefore we can say it's 4x minus 10 e to the power of x plus 2x squared plus 8x plus 11 would be our overall solution of the problem.